Okay, so today we are going to do analysis of circuit with still with one energy storing element, yeah, with constant independent sources. So this means that they are not changing with time. So, and this is still one energy storing element, so it means it can still be solved using first degree differential equation. First order differential equation. Let's learn now how to solve it step by step. So of course, until by this time you are already quite familiar with this form of solution, yeah, of the parameter in that circuit, yeah, either voltage or current xt, yeah, which is now expressed as xt, a general variable xt. Xt equals to k1 plus k2 exponent minus t over tau for t larger than 0. So this approach relies on the known form of the solution, but finding the constants k1, k2, and tau using basic circuit analysis tools, and then forgoes the determination of the differential equation model. So basically, you use first the basic circuit analysis tool to derive the general form of equation, which you should try to make that equation from the basic circuit analysis tools to conform to the standard form, yeah, of the first differential equation. From there, you can easily calculate the tau, then you can calculate the k1, which is the steady state, the constant, yeah, the steady state solution, and the k2. K2 is the constant which you will get from the steady state solution and the transient solution. Yeah, K1 is the steady state value of the variable, can be determined by analyzing the circuit in a steady state. And the initial condition is usually given by the problem, So with these initial conditions, x0 plus, then you can compute the constants k1 and k2. Okay. Tau is the time constant, and then it can be determined using the Thevenin across the energy storing element. For example, here we have a representation of an arbitrary circuit with one storage element. It could be inductor or capacitor, and it is connected to a Thevenin representation, a circuit with resistances and sources. So this circuit with resistance and sources you can express using its equivalent Thevenin theorem, yeah, consisting of VTH, the Thevenin equivalent voltage source, in series with the Thevenin equivalent resistance RTH. Then they are connected. It is connected to the inductor or capacitor at the terminal A and B. So from here, then you can calculate. You can use the Kirchhoff's current law. It's like this: Kirchhoff's current law at the node A, yeah, VC and then IR, and similarly also in the case 2, current through the inductor. For the case with capacitor, KCL at node A, we obtain IR plus IC equals to 0, IC equals to C dV dt, yeah, the differential form of capacitance law, and IR equals to the VC here minus VTH divided by RTH. Okay, so substituting these two values of IC and IR into the original Kirchhoff current law equation, we will obtain C dVc dt, okay, plus Vc minus VTH divided by RTH equals to 0. So this is the general. From here, then you change further, yeah, to the general form that confirm compatible, yeah, to the general form of first order differential equation. You multiply each term with RTH. So this becomes RTH C dVc dt plus Vc equals to VTH. Okay, yeah, that is like this. So here you obtain the tau from this value RTHC. Then you can obtain the K1 from the steady state value here, VTH, then you can obtain based on the given initial condition, then you can calculate K2. Okay. At the inductor case, you use KVL, Kirchhoff voltage law. Yeah, VR plus VL equals to VTH. Yeah, since VR equals to the Thevenin resistor value times the current of the inductors, IL, while the VL you can calculate using the differential form of the inductor's law. VL equals to LdIdt. So here one point that you need to take remark here, that why don't we use KCL? If we use KCL here as like this, then we will be forced to use the integral form, yeah, of the inductance law. Yeah, although eventually, yeah, we may get the same first order differential equation, but that form of inductance law is usually not easy to solve. You have to derive first, yeah, in order that you can get the first order differential equation. If it is integral, then it means you have to derive 2 times. Yeah. It will be easier if you use KVL here, then just use immediately the differential formula of the inductance law. So VL equals to L dIL dt. So VL equal to dIL dt plus VR equals to the VTH. So then your obtained equation, the obtained equation from this Kirchhoff voltage law, yeah, will be resembling the first order differential equation format. Yeah, we just then divided each term with RTH, so this become L over L divided RTH times the ILDT plus IL equals to VTH divided by RTH. So this is already in the standard form of first order differential equation. L over RTH will become the tau, and this part becomes the K1, yeah, the steady state solution. Yeah, so here from here basically VTH divided by RTH equal VTH divided by RTH equal the ISC, or the Norton equivalent source. Okay, and if you compare the two, if you use inductor, so your equation, the x, yeah, the tau dx dt plus x equals to the forcing function. In the inductor case, you use KVL, the x will be the current flowing through the inductor. In the capacitance case, here it will be voltage across the capacitor. Okay. So for capacitive circuit, the tau will be RTH times C. For inductive circuit, the tau, the time constant, will be L divided by the Thevenin resistor. Okay. Okay. Let's continue. So you obtain now the form of the solution from after obtaining the this general format, yeah, the general form of first order differential equation, which then you can express the solution in this form, yeah, xt equals to k1 plus k2 exponent minus t over tau for t larger than 0. K1 here is obtained from the steady state equation, steady state solution. In this case, this is x at infinity. So when x at infinity, in this case, then the variable change over time will be 0. So the ILTT equals to 0. This is also equals to 0. At that time, then it will be equal to the forcing function at the right-hand side of the equation. Okay. While the K2 can be calculated from the obtained K1 and also the given initial condition x0 plus. Okay. That's why then you need to determine the x0 plus, this initial condition. Draw the circuit. To obtain this, you have to draw the circuit in the steady state prior to the switching, before the switching, and then determine the capacitor voltage or the inductor current. After that, you draw the circuit at 0 plus, where the capacitor will act as a voltage source, okay, and the inductor acts as a current source. So then you will determine the variable at t equals to 0 plus, so after the switch is turned on. To determine the X infinity, you draw the circuit in steady state after the switching and determine the variable in the steady state. Finally, determine the time constants, basically from the tau, yeah, at the standard form of the differential equation, yeah, which is usually basically the coefficient of the first order differential term. In the case of capacitive circuit, it will be RTH times C. In the case of inductive circuit, it will be L divided by the inductance value divided by RTH. Then determine the constants K1, K2. K1 will be the X infinity, the response, the variable at T approaches infinity, and K1 plus K2 usually equals to the initial value. Let's give some example here. Find the current IT when T is larger than 0. The circuit is like this. So initially, before T equals to 0, yeah, the switch is off like this. Yeah. So when we look at this circuit, the capacitance is being charged, right? It is being charged. When this is turned on, okay, when this is turned on, yes, yeah, capacitance is being charged. When this is switched on, this is connected, this is short circuited, all the current will flow through here. Now let's see. Let's express the here the what is being asked is the current IT. So we express this in the general standard solution form. IT equals to K1 plus K2 x1 minus T over tau at T larger than 0. But then we need to first calculate the initial voltage across the capacitor. So when this is not switch on, so this is switch on. So we draw the steady state condition prior to switching. So this will be drawn as open circuit. Yeah, so this is drawn as open circuit. We will obtain, this is basically a voltage divider circuit. Okay. So we can calculate the current here. The current will be 36 minus 12 volt because they are opposite polarity divided by the series resistance. Yeah. 36 minus 12 volt is 24 volt divided by 2 plus 6 plus 4, which is 12 kilo ohm. We obtain the current to be 2 milliampere. Okay, 2 milliampere. And this is the current before the switch is turned on. Using KVL here, then we will calculate VC equals to 36 volt minus 2 kilo ohm times the current. Yeah. 36 volt minus 2 milliampere times 2 kilo ohm, which is 24 minus 24 volt. 36 minus 24, sorry, 4, yeah, 4 volt. 36 minus 4 equals to 32 volt. The VC here equals to 32 volt. The steady state before the switch is turned on. So, as we know in capacitance that the voltage is continuous, so the voltage at the capacitance just after the switch is turned on should be equals to the voltage of the capacitance just before the switch is turned on. So this is expressed mathematically like here. VC at 0 plus, at T equals to 0 plus equals to the VC, the voltage capacitance at 0 minus. Step 3, let's determine now the current flowing at 0 plus. Use a circuit valid for T equal to 0 plus. So when this switch is just turned on, the capacitor now will act as a source because this is turned on. Voltage will the charge voltage from the capacitance will also flow. So this voltage, yeah, just after it's turned on, the voltage of the capacitor is 32 volt, yeah, because due to the continuity law for the capacitance. Now this is short circuited, so no current flowing through this part of the circuit. Yeah, all current will be just flowing like this. Okay. So the I0 plus here will be equals to the default divided by 6 kilo, because this is now grounded, and this is grounded to 0. So the current flowing through here is the default divided by 6 kilo ohm, equals to 16/3 milliampere. For inductive circuit, determine the initial inductor current in step 2 here. For the t equal to 0 plus, the circuit is replaced inductor by a current source instead of voltage source, because in inductor what is continuous is the current, not the voltage. Okay, the step 4 now is to determine the current when t approaches infinity. So this is the original circuit shown here at the bottom right. Use the circuit in the steady state after switching. So after the switching, eventually the charge will be depleted from the capacitance, so it will turn back into an open circuit again. But however, this is now already short-circuited here. Okay, so the I infinity here will be this 36 volt divided by 2 plus 6 kilo ohm, or 8. Yeah, because no current flowing through here, because this is short-circuited. If it is short circuit, all current will flow through this wire. Yeah, nothing will flow through this. So 36/8 milliampere. Then let's determine the time constant. Okay, so let's go back. Oh yeah, this is the current. What is being asked is the current flowing through the 6 kilo ohm resistor. Yeah. So this is capacitive circuit. The tau will be equal to the Thevenin resistance times the capacitance, like this. So let's find, this is the terminal A and B. Let's find the Thevenin resistance. So the voltage source here becomes short circuit. Yeah, remember again the Thevenin theorem. To find the Thevenin resistance, we short circuit any voltage source and open circuit any current source. So this is short circuited. This is short circuited. The Thevenin resistance is seen from these two terminals. Okay, so it means that these are in parallel with this. Yeah, and so since this is short circuited, this can be considered as short circuit as well, yeah, because it is already grounded. So the Thevenin parallel, the Thevenin equivalent resistance will be 2 kilo ohm parallel 6 kilo ohm, and we obtain 1.5 kilo ohm. The capacitor itself is 100 microfarad, so we obtain the time constant. Yeah, 1.5 kilo ohm times 100 microfarad, we obtain 0.15 second. Now, let's determine the K1 and K2. Step 1, IT equals to K1 plus K2 exponent minus t over tau t. At I, just after the switch is turned on, or I0 plus, yeah, the current is 16/3 milliampere. Again, where that is come from? Let's see the previous slide. This one, yeah, it comes from here. So this is when the switch is just turned on. So the capacitance voltage is equal to the capacitance voltage just before the switch is turned on. So then we obtain the current here to be 16.3 milliampere. And this will be equals to K1 plus K2. Yeah, this is the current at 0, the initial condition. The initial condition, remember, equals to K1 plus K2. The current at infinity is already calculated also here. Yeah, at steady state, at time equals approaches infinity. So we model again the capacitance as open circuit, 36/8 milliampere. This is K1. Then from here we can calculate K2 to be equals to 16/3 minus 36/8. We obtain K1 K2 to be 5/6 milliampere. No, just yeah, just in milliampere also the unit will be milliampere. So the final answer, we insert back the values of this K1 and K2 into the basic form or the standard form of the solution. IT equals to 36/8 here. Yeah, the K1 plus 5/6 K2 times exponent minus T over tau. The tau is here 0.15 second. Okay, any questions for this? It's quite clear, yeah? So let's review back. Basically, you obtain the initial value, you have to calculate the voltage of the capacitance just before the switching. Yeah, so let's review the previous slide. Yeah, to obtain the initial value I is 0 plus, you have to obtain the here first is this one, the circuit in steady state prior to the switching, in order to obtain the VC just before the switching, which will be equal to the VC just after the switching. Then from here, then you can calculate the current I0 plus the current flowing just after the switching. Then to obtain the current that flows at infinity after it is being steady state, after being switched on, then you redraw again in the steady state circuit after switching. So in this case, this is drawn, capacitance is drawn again as an open circuit, but now it is short circuited here because of the switching. In this, you obtain the I at infinity 36/8. Then you can determine the time constant, yeah, like this, by calculating the Thevenin, the equivalent Thevenin resistance of the surrounding circuit, yeah, at the terminal that connects to the capacitance. Then you obtain the tau. The K1 and K2 can be calculated from the initial value, yeah, of the I, the current, the I0 plus, and the steady state value or I at infinity. Okay, like this. Okay, is there any questions so far? I think it's quite clear. For inductive circuit, on the other hand, the value of the time constant will be the inductance value divided by the RTH. Okay, so this is when you are asked to display using MATLAB or Octave. Yeah? So you obtain when the current before T equals to or less than 0 is 2 milliampere. So like this, when T equals to 0 is 1, 36/8 plus 5/6. So you obtain 2 milliampere. And at T larger than 0, this is the value. So this can be generated, can be programmed like this. To lin space is to generate linearly spaced vector between x1 and x2. If you don't put the number of points, it will consider it as 100. Yeah. Then like this. Then you can calculate here is this I minus here is the current before the T equal before 0. So this T when T is less than or equal to 0, 2 milliampere. Yeah, 2 times 1. So I still this. The I plus here is from this formula 36/8 plus 5/6 times exponent minus T plus, yeah, T plus here is from 0 until the end. Yeah, then here is 10 times tau, when we consider that the error between the value to the steady state value is very small already. Minus t divided by tau. And plotting from t minus until t plus. Yeah. Yeah, this is the plot I minus, and then the plotting the I plus. Okay, so this is the result. So before t equals to 0 at the negative value, the value of the current is 2 milliampere. Then after the current is switched, after the switch is turned on, the current becomes like this. So the infinity is 4.5. Is it correct? 4.5. The infinity current is 36.8, or more or less about 4.5 milliampere. Yeah, 4.5 milliampere. Yeah, like this, the steady state value. Okay, any questions? Not yet? Okay. Another example here. Now we have inductance for Henry here. Find the Vt at t larger than 0. Yeah, this is connected like this. Vt here is the voltage across the 4 ohm. Across the 4 ohm resistor. There's one steady state, one voltage source, 24 volt. Here, initially it is not switched on, yeah, but at t equals to 0, it is switched on. The switch is turned on. Okay, so Vt we express in the standard solution form of differential equation, first order differential equation. Vt equals to k1 plus k2 exponent minus t over tau. And then we set the initial inductor current, yeah, the initial inductor current here. And we redraw the switch, the circuit as steady state circuit. So then it means the inductor is drawn as short circuit, yeah, connection. Like this, the current flowing through the inductors is here. And so if we see here, this 1 ohm is connected like this. This is 3 ohm, and this is basically the same node, yeah, since this is short circuited. This is the same node, yeah. And then it becomes, the resistor here becomes 6 kilo ohm in parallel with 3 kilo ohm. So the current flowing through here, yeah, which is 2 ohm, right? 6 kilo ohm in parallel with 3 kilo ohm is 6 times 3, 18 divided by 9, 2 kilo ohm. So the current flowing through here is 20 ohm. It means then there is no current flowing through the 12 ohm resistor, yeah, because this is already short circuited. The current one here equals the current flow here to the 4 ohm resistor equals to, as well as through this one. No, just through this the main branch. 24 divided by 4 plus 2 kilo ohm or 6 kilo ohm. Yeah, so the current is 4 milliampere. Okay, the current at the inductance just before the switching, it will be equals to the current flowing through this branch, yeah, through this branch. And then we can use the current division formula, current divider formula. So 6 over 6 plus 3 here times this current 4 milliampere. 6 over 9 is 2/3 times 4. Yeah, equals to 8 over 3 milliampere. This is the current over the inductance just before the switching. Now, when we now determine the voltage just after the switching. Just after the switching, according to the continuity law in inductance law, yeah, the current should be continuous. So it means the current at the inductance flowing through the inductance just after the switching should be equal to this current through the inductance just before the switching. Okay, use the circuit at t equals to 0 plus. Inductor here is replaced by a current source. So the current here flowing through the inductor is 8/3 milliampere. This part, right? This is milliampere actually, not ampere. So mistake in the unit. Okay, so using Kirchhoff voltage law, Kirchhoff current law (KCL) at this node, so we will obtain here V1 minus 24 divided by 4 plus V1 minus V1 over 6 here plus V1 over 12 because this is grounded. This is connected to the ground. Yeah. Since now it is switched on. Yeah, it is now switched on. That's why it is now connected to ground. Short circuiting the circuit at this node. Plus 8/3. Yeah, equals to 0. 8/3 ampere. Now it becomes ampere. So from here we will obtain the V1 to be equals to 20/3 volt. From this equation, Kirchhoff Kirchhoff current law, we obtain V1 equals to 20/3 volt. Okay. So the voltage, this is 20/3. Voltage across this 4 ohm resistor will be 24 volt minus V1. Yeah, 24 volt minus 20/3. So equals to 332/3 volt. So we have determined the voltage, the initial voltage condition at t equal to 0. Now we determine the voltage when the time is at infinity, so at steady state. So we redraw again the circuit at steady state. Yeah, when t equal to infinity, but now the switch already turned on. So we redraw again the inductors as a short circuit wire like this. Yeah, but this is also short circuited. So it means this now is grounded. Okay, the voltage across here will be equals to this voltage, 24 volt. Yeah, because this is grounded. The voltage at infinity will be equals to 24 volt. Determining the time constant, we have to determine now the Thevenin equivalent resistance at this terminal. Yeah, the inductive circuit like this. What is the RTH here at this point? Yeah, the voltage source is short circuited. Okay, it becomes like this. So this is in series, right? This is in parallel with this, and then it's not easy to solve like this. You have to redraw. If necessary, you can redraw. Yeah, this is drawn as a single node here. So it means these 3 resistors are in parallel. These 3 resistors are in parallel. 4, parallel 6, parallel 12, which then they are. This is not considered anymore, yeah, because this is short circuited. This is already grounded. So we only obtain from this 4, parallel 6, parallel 12. 1/4 plus 1/6 plus 1/12. So equals to 3/12 plus 2/12, which is 3 plus 2 is 5 plus 1, 6/12. So the RTH equals to 12 divided by 6 equals to 2 ohm. Okay, 2 ohm. So from here we obtain the Thevenin resistance equals to 2 ohm. The inductance is 2 Henry. Yeah, sorry, 4 Henry, right? The tau will be L over the RTH, 4 Henry divided by 2 ohm equals to 2 seconds. Now we determine K1 and K2. K1 will be equals to the volt at infinity, yeah, which we have calculated here. The volt at infinity here equals to 24 volt. The voltage at 0 plus, yeah, the initial value, which equals to 52.3, 52/3 volt, which we have calculated in the previous slide. This equals to K1 plus K2. K1 itself equals to this one, 24 volt, and this is equals to 24, yeah, minus 52.3. Yeah, this is the initial value, 52.3 minus K1. K1 is here, 24 volts. So we obtain K2. Yeah, this is K2 to be 20 over 3. Minus 20 over 3. Wait, this is supposed to be 52. K1. Oh, this is K1. Yeah. Let's see. The standard form. K1 plus K2 exponent minus T over tau. The initial value is 52 over 3 volt, right? 52 over 3 volt. So the steady state value is 24 volt. So the steady state is supposed to be K1, right? The steady state is to be the K1. Yeah, this is correct, 24 volt. So the K2 is from here, 50 to 3 is the initial value. K1 is known, so this is supposed to be K2. K2, so this is supposed to be K2. 52 over 3 minus K1 minus 24 volt equals to minus 22. So yeah, this is something wrong. Yeah, actually this is supposed to be K1 is 24, then minus 20. This is K2, right? Minus 23 over the exponent minus T over 2. Any mistakes here in this circuit, in this solution. Okay. Okay, let's do another example. So please take in mind, yeah, this is not, it's like it's supposed to be this one, because the 24 here is the K1 and the K2 is minus 20 over 3. Another example here, find the V output of T when T is larger than 0. So when T is larger than 0, the switch is turned off. The switch is turned off. Yeah. Like this. So initially, so let's draw now. The question is V output here. V output T equals to K1 plus K2 exponent minus T over tau, expressed in the standard form of differential equation, the first order differential equation. Calculate first the initial capacitor voltage across the 2 farad capacitor here. So we draw this as open circuit. Okay. So this is still switch on. So at T less than 0 is like this. So the voltage across this will be, yeah, DC plus. This is 12 volt. So this is V1. Okay. Using Kirchhoff current law here. At V1, V1 minus 12 divided by 3 here, plus V1 minus 8 divided by 2 ohm, plus V1 minus minus 0 here divided by 2 ohm equals to 0. Then we multiply with 6, so we obtain here, this is 2 V1 plus 3 V1, 2 V1 plus 3 V1, 5 3 1, 5 V1 plus 3 V1 equals to 8 V1. Then minus 48 equals to 0, where we obtain V1 to be equals to 6 volt. Then the V output here, VOT here, the V2 will be equals to 2 volt. Yeah, from here is 2 volt. The V1 is 6 volt. This is 12 volts. So 12 minus 6 is 6. So this is a voltage divider, basically, to 2 over 3, 2 volt. So the VC at the 0 just before the switch is turned off should be equals to the VC at just after the switch is turned on, at 0 plus. So this is equals to 10 volt. The VC will be here. The VC is here is equals to 10 volt. 6 volt. This is V1 equals to 6 volt. Then the current flowing through here is 12 minus 6 equals to 6 divided by 3 divided by 3, 6 divided by 3. Let's just do some small simple calculation. So V1 equals to 6 volt. So here the current flowing through here will be 12 minus 6 divided by 3. 6 or 4 ampere, 4 ampere. So the V2 will be 1 ohm times 4 ampere. Anyone knows here why is it 2 volt? It's supposed to be 4 volt. Anyone can pinpoint? If any idea? Otherwise, we go stick for the slide first. So the VC here, it's this one, this condition. So if V2 is 2 volt, then the VC will be 12 volt minus 2 volt. 12 volt minus 2 volt equals to 10 volt. So now we determine the V output just after the switch is turned on. So we replace the capacitance with the voltage source 10 volt like this. Okay. Now we calculate the initial condition at this 2 ohm. So V output here, and this is switch off. So this is a voltage divider. 2 divided by 2 plus 2 times 10 volt. So equals to 5 volt. Now we determine the voltage at the 2 ohm at infinity, so at steady state. We redraw again the capacitance as an open circuit, and this is now also open circuit. So the V output at infinity here will be equals to, this is also another voltage divider, 2 ohm divided by 2 plus 2 plus 1, or 5, 2 over 5 times 12 equals to 24 over 5 volt. We determine the time constants that is connected to the capacitor. Okay, so then we determine first the Thevenin equivalent resistance. Here we short circuit this voltage source. We short from here, this is open circuit. Okay, so the resistor seen from this terminal will be this 2 ohm in series with this 2 ohm, 4 ohm, in parallel with this 1 ohm. Okay. And 1 ohm in parallel with the 4 ohm. We obtain 4 over 5 ohm. So since the capacitance is 2 farad, the tau will be 2 times 4 over 5 or 8 over 5 seconds, or 1.6 seconds. Let's determine the K1 and K2. K1 is the steady state response when the V output is at infinity. So K1 here is 24 over 5 volt. Initial value is already calculated from this one. Initial value is 5 volt, and this is equals to K1 plus K2. So 5 volt equals to 24 over 5 volt plus K2. So from here we obtain K2 equals to 24 over 5, 5 volt minus 24 over 5, or 1 over 5, 1 over 5 volt. So then we can express the V output here equals to 24 over 5 plus 1 over 5 exponent minus t divided by 8 over 5 volt. Okay. Are there any questions so far? Okay, so Since time is up for the first hour,